Welcome to the topic 1.5.1c Stack Frame Analysis, Stack Creation. From a programmer perspective, the global variable int m and the local variable int n are accessed in the same way. M is equal to 4, n is equal to 5. But when the system allocates memory for the global variable and for the local variable, it will be different. For the global variable, it is static allocation, but for the local variable, it is dynamic allocation, but it is implicit. The programmer will not know when the memory is allocated for a local variable. This is the differentiator. The size is same, but the allocation of memory for the local variable it is dynamic and implicit. For the global variable it is static and fixed. This differentiator drives the compiler to generate instructions for accessing data. How does the compiler generates instruction to access data? Local variable and global variable. For global variable, since it is fixed and static allocation, it generates an direct address, but for the local variable it has to generate a relative address. How that relative address is generated? We have seen that in the earlier session. The relative address is always from with respect to the start of the frame, stack frame, or with reference to the end of the stack frame. How the compiler does that exactly? Will it take the help of the processor? Will the processor provide some means for the compiler in the entire mechanism of addressing local variables? All those gory details we will be looking in this session. To continue with, let us look into the picture of the program and its sections. Program having code which is having fixed size, static and implicit allocation. Data, fixed size, static and implicit allocation. Heap, the size is dynamic and explicit allocation. Stack, fixed size, dynamic and implicit allocation. This is a differentiator for our discussion, right? For the data, you have a fixed size code, static allocation just before the start of the program, and implicit. Programmer doesn't know how the allocation happens. Fixed size, the code is fixed. Dynamic allocation just at the time of invocation of function, and implicit, programmer is not asking for explicitly for allocation of memory for stack local variables, right? This will have a bearing, static and dynamic. This is having a bearing on how the compiler generates instructions. Here we go. Code, accessing data through direct addressing, and heap and stack through indirect addressing. The focus of this session will be on relative addressing, right? Relative to what? The compiler generates an address to access the local variables relative to the start of the stack frame or end of the stack frame. We will see that, right? Now, getting into the details, we will zoom in the stack segment of the program's memory layout and see how does the compiler generates the address. What are the contents we have, right? This is the code. This is what we are telling. Code is fixed, then the number of variables is fixed, their size is fixed, right? The allocation of the memory will be dynamic. Only at the time of invocation of this main function, we have local variables and we have arguments, function arguments, right? When this function is invoked, everything will be in the current stack frame. This is the stack boundary, start of the stack frame, end of the stack frame, right? The access to these variables will be with respect to start or end. We will see that, right? Who builds the stack frame? before that, we will look into the anatomy of a function. Will the function contain only the code written by a programmer, or will the compiler add something to that? Now we will be referring into the compiler translated function. What we have written is a high level C code. Now what compiler generates an assembly code. When the compiler generates a assembly code, the anatomy of the function will be like this. The compiler adds the prologue and epilogue part. We will see what it is. Prologue part will be placed by the compiler to set up a stack frame, designates the memory required for local variables, underline the word, mark my words, designates. Compiler will not allocate, only prepares the stack frame for the allocation, and the allocation is done by the kernel at the time of execution of the function, or just prior to the start of the function. The body of the function is exactly what is written by the programmer, and the epilogue placed by the compiler for the complementary action of the prologue. Stack is set up here. The unwinding action takes place at the epilogue. Now we will look into the help got by the processor. Processor helps the compiler in building the stack frame as well as managing the stack frame. How is it going to help? By providing certain exclusive registers for the stack operation. The common and well-known stack uh, uh, pointer register, or the register which is useful for stack operations, is ESP, right? And this is, as usual, it's a program counter. And haven't I remember about this EBP now, which is part of a general purpose registers used for arithmetic operations or mathematical operations, right? But this will be of important use in this context. Please remember that, right? Next, now we will be looking into the details of the instructions. We have taken this code, right? Very simple code. Don't look into the logic of this code, right? The intention is to only understand the stack frame in this context. So we have not paid much attention into the logic of the code. Now the compiler translates this function f1 into these instructions. This is a assembly code which is getting translated into this machine code, right? Now what is the prologue of this code? This is the prologue, just cre creating or designating for creation of stack frame. Subtract ESP, right, from the ESP value to 0x10, 16 bytes. That means the stack frame is of 16 bytes. See here, pay attention here. The address of the parameters m and n are referenced with respect to the stack pointer. That is what we were referring as relative addressing. In the next slide you will be uh, uh, getting more with the pictorial representation. Again here, the next variable n is accessed through ESP. ESP plus 18, you get you are moving the value to the EAX, right? This is how it is referencing the memory where the value of m and n are stored, right? If you print the address of m in the program, you will see the address got by ESP plus 14. Address of n is got by ESP plus 18. This is what is relative addressing. And what is the epilogue of this? This is the epilogue, and this part of the program is actual body of the program written by the programmer. That is right. Now what does the uh, epilogue do? Just to do a complementary action. Here we compiler does subtraction, here it does then addition, and the return instruction. This is extra help provided by the processor. Processor hand in hand with the compiler, right? Call instructions. When a call followed by the address is generated, this is what the compiler does. Push the EIP, the next address, into the stack, and then this operand is moved to EIP. That means when a call instruction is issued, the execution control immediately should jump into this address, right? And then the execution follows. When the return instruction is executed, the the processor provides this operation pop EIP. That means the return address which is stored as part of the call instruction is again popped back into the EIP so that the execution resumes from the calling function. This will give a better visualization of what we were discussing in the previous slide, right? Here we have a picture. See now, when the call instruction is issued, the processor pushes the EIP value to the stack, right? And then moves the operand into to EIP register so that there is an immediate transfer of execution control to the called function. And then body of the function is executed, and then the complementary action followed by return again pops the EIP value in pops the return address, right, present in the stack to the EIP value, right, so that the execution resumes from the calling function, right. Now let us see how uh, to make the compiler generate the code only using ESP register, right. This is how we make the compiler generate the prologue and epilogue using only ESP. We have to specify this option, right, so that you will get to the code what we saw in our previous slide. Now we will look into the pictorial representation for having a better visualization. This is how the stack frame was created, right. As part of the call instruction, the return value is pushed, right, and after that the ESP will be uh, pointing to the end of the stack frame. The next stack frame, the same thing, and the ESP will be pointing to the end of the stack frame. Next stack frame, same thing. Now this was absolutely fine. The problem was when the program crashes at the function associated to this stack frame. The compiler, the debugger was very novice in the mid 90s, such that when we had to do a backtrace, when we had to inspect the earlier stack frame, it was not possible because with the current stack frame, the debugger was unable to move to the previous stack frames, and we would for a further analysis, the programmer was handicapped to look into the earlier stack frames to investigate what was the reason for the application to crash. Basically, the debugger was really novice. Now, the debugger went back to the compiler requesting for more information. What is that more information? It requested that somehow provide a link from this stack frame to the previous stack frames so that it will be helpful for a programmer using the debugger to look back into the earlier stack frames. So what was the requirement put forth by the debugger for the sake of programmer is this. He wanted a link back to the earlier stack frame. So this was in principle the request posed by the debugger, right, for the back tracing of the earlier stack frames. How did the compiler provision that? Again, will the processor again come in handy for the compiler? Let us see now. Using base pointer register for stack creation and stack operations, right? I earlier pointed out to have a eye on EBP, the base pointer register provided by the processor. Now we will see use of EBP for stack creation and management. Now pictorially we will see how the compiler used EBP to honor the request by the debugger. So it also used one more register called EBP to hold the starting address of the stack frame, right? Further, when the next frame is created, stored the address of this stack frame in the next stack frame. This is how it does. Stored the address of the previous stack frame here. So debugger will have a link for the previous stack frame. Again, when the next stack frame is created, stores this address of this current stack frame in the next stack frame. This is how the compiler helped the debugger to backtrace. Right? Again, the compiler takes the help of the processor in the form of register. Right? We will look into the details of the prologue now. The compiler, same function. How does the prologue look like here? Now it has uh, two extra instructions now. Push EBP. This will store the previous stack frame's address in the current stack frame. Move ESP to EBP. Now setting the starting address of the stack frame into EBP, and now again designating the memory for the stack frame. How does epilogue look like? We have one more instruction called leave. What will it do? Leave will again move the EBP value to the ESP, unwinding of the stack frame, and then pop the EBP value so that the previous stack frame is restored. And again, this we have seen the return address is popped to the EIP. What does the call do here? Same thing, call as no change of what we discussed in the earlier sessions, right? To have a better visualization, we have for this code assembly code as well as the pictorial representation. Same thing, right? It is self-explanatory after we have seen in the earlier session, right? The return address is popped back, right? This is how again processor comes in handy for the compiler for the to manage the stack operations, right, from creation to unwinding and backtracing, right? Now let us have a new look with the perception of the linked list. We have understood, written, comprehended this kind of a linked list where we have a node, we have a pointer to the next node, and again we have a pointer to the next node. So if you see the stack creation with an eye of a linked list, this is how the stack is implemented. Again, it's a linked list. This is the first frame. The next frame will have a pointer back to the previous frame, and again this frame will have a pointer back to the previous frame. If you can implement this kind of a linked list, then you would have been in a better position, or you will be in a better position to understand the stack creation, right? I think we are nearing to the end of this session, and as usual, this is the OS information. What we have used to experiment uh, with all the small programs and whatever we are showing in this session, right? What next? We have come too far into the stack, and next is a beautiful animation of stack operations, right? The entire stack discussion, whatever we had for the past 3 sessions, will be beautified through an animation. Exactly see how the dynamics or the acrobatics of stack operations through animations, which will leave no stone unturned for your understanding, right? With that, we come to a conclusion, and till we see you in the next session, take care and bye bye. If you have any questions, any doubts, comments, and feedback, please don't forget to post it in the video page.